Picture this, a planet where familiar coastlines dissolve into deep blue, where entire continents slip beneath the waves, and where the very ground beneath ancient civilizations vanishes as if it were never there. This isn't a scene from a fantasy film or a distant future. It's our own world, reshaped by forces far beyond human control. What if I told you that Earth's gentle tilt, that subtle lean in its spin, set off a chain of events so profound that oceans redrew their borders and rewrote human history? This is the story of how a wobble in space drowned cities, inspired myths, and forced entire cultures to adapt or disappear, and it's a story that's still unfolding today. Deep within ice cores drilled from polar caps, locked in layers of ancient ocean sediment, and whispered in flood myths passed down through generations, lie clues to a past that feels almost unimaginable. Civilizations rose on lands that no longer exist. People built homes, temples, and communities along shores that would one day be buried under hundreds of feet of water. And it all happened because Earth's axis tilted not suddenly, but significantly enough to redirect sunlight, melt massive ice sheets, and send sea levels climbing at a pace that would feel catastrophic to anyone living through it. These weren't slow, gentle changes. They were planetary turning points that determined which species survived, which cultures thrived, and which stories would be told for thousands of years. In this video, we're going to unravel those mysteries together. We'll travel from the submerged ruins of lost cities to the frozen archives of Antarctica, tracing how Earth's tilt triggered climate chaos and rewrote the map of our world. You'll discover why this ancient drama matters today more than ever, as modern science reveals that the same forces that drowned Doggerland and inspired tales of Atlantis are still at work, influencing everything from global weather patterns to the stability of our own coasts. By the time we're done, you won't just see the planet differently. You'll understand the fragile, powerful dance between Earth's orientation and the oceans that define so much of life as we know it. This is a journey into the deep past, but it's also a window into our future. So what exactly is this tilt, and how does something so seemingly small set off such massive changes? Think of Earth not as a perfect spinning top, but as a slightly off-kilter globe leaning at an angle of about 23.5 degrees. This isn't a static, fixed position. It's more like a slow, rhythmic wobble over vast stretches of time. The gravitational tug of war from our moon and even other planets in our solar system constantly nudges our planet's orientation in a process known as axial precession. This gentle sway might seem insignificant on a human timescale, but over thousands of years, it dramatically rewrites the rules for where and how intensely sunlight strikes the planet. This redistribution of solar energy is the real game changer. When the Earth's tilt is more pronounced, the polar regions get bathed in significantly more sunlight during their summers. This isn't just a minor temperature increase. It's enough to trigger the large-scale melting of massive ice sheets that have taken millennia to form. All that locked-up water has to go somewhere, and it flows into the oceans, causing sea levels to climb dramatically. Conversely, during periods of a lesser tilt, the poles receive less intense solar radiation, allowing ice sheets to expand and advance, locking away ocean water and causing sea levels to fall, sometimes exposing vast stretches of land that were once submerged. We know all of this not just from theory, but from concrete evidence hidden in nature's own archives. Scientists meticulously study ancient coral reefs that now sit high above modern sea levels, their fossilized structures marking where the ocean surface once was. They drill deep into ocean floor sediments, pulling up cores that contain layers of microscopic fossils and chemical isotopes. Each layer is like a page in a history book, recording past temperatures and the volume of ice on the planet. By reading these natural records, researchers can pinpoint times when even a slight shift in the Earth's tilt led to profound changes, flooding entire continental shelves or creating land bridges that allowed species, including early humans, to migrate across the globe. This entire mechanism is the foundational key to unlocking the mystery of why oceans have, throughout deep history, risen to swallow vast territories and then retreated to reveal them once more. But that slow wobble of Earth's axis doesn't operate in a vacuum. It's part of a much grander celestial timekeeping system. This brings us to the brilliant work of a Serbian scientist named Milutin Milankovic. In the early 20th century, while much of the world was engulfed in war, Milankovic was immersed in a different kind of battle, a painstaking mathematical quest to solve one of the planet's greatest puzzles. He was determined to calculate the precise ways in which variations in Earth's journey around the Sun could dictate its climate over immense stretches of time. His theory, now foundational to our understanding of paleoclimatology, describes a set of rhythmic orbital cycles that act like a complex cosmic clock, meticulously winding Earth's climate up for an ice age and then down for a warmer period. These Milankovic cycles are essentially three distinct, overlapping rhythms in our planet's motion. The first is called eccentricity, which is the change in the shape of Earth's orbit around the Sun, shifting from a nearly perfect circle to a slightly elongated ellipse over a cycle that lasts about 100,000 years. This alteration changes our distance from the Sun at different points in the year, subtly influencing the intensity of the seasons. The second rhythm is obliquity, which is the variation in the tilt of Earth's axis itself, oscillating between about 22.1 and 24.5 degrees over a 41,000-year period. This is the cycle that directly controls how extreme our seasons are. A greater tilt means more pronounced differences between summer and winter. The third cycle is precession, often described as the wobble of a spinning top. Over a 23,000-year cycle, the direction in which Earth's axis points slowly rotates, changing which star we call the North Star, and more importantly, determining whether the northern or southern hemisphere experiences more intense seasonal contrast. The true power of this system isn't in any one cycle operating alone, but in their occasional, powerful alignment. Picture these three slow-turning gears in a massive machine. For tens of thousands of years, they turn out of sync, their effects partially canceling each other out. But then, they slowly fall into phase. When a period of high eccentricity coincides with a greater axial tilt and a specific precessional orientation, the combined effect can be dramatic. These are the moments that kick-start or end ice ages. They amplify temperature shifts to a tipping point, causing continental ice sheets to either rapidly advance, locking away ocean water and lowering global sea levels, or to catastrophically retreat, releasing torrents of meltwater back into the oceans. This celestial clockwork is the master script behind the dramatic rewriting of the world's coastlines. A shift toward a lower axial tilt, for instance, means the polar regions receive less intense summer sun. This slight reduction in solar energy is enough to tip the balance toward glaciation. Winter snowfall begins to outpace summer melting, and ice sheets gradually grow thicker and spread farther, siphoning water from the oceans and causing sea levels to drop, sometimes by hundreds of feet. This is how land bridges like the one connecting Asia and North America emerged, creating highways for life. Conversely, a shift toward a higher tilt bathes the poles in stronger summer sunlight. The ice can no longer withstand the heat, and the great melt begins. This is the flooding mechanism that submerged continents like Sunderland and drowned the fertile plains of Doggerland, transforming the map of the world and forever altering the course of human migration and civilization. It's a breathtaking demonstration of how the slow, predictable motions of our planet in space direct the most profound environmental changes on its surface. So how do we move from the theoretical brilliance of Milankovich's calculations to the tangible, physical proof that Earth's axis has indeed wobbled and reshaped our world? The answer lies frozen in time, buried deep beneath the ice of Greenland and Antarctica, and layered on the ocean floor. These are not just inert piles of snow and mud. They are the planet's most meticulous and faithful archivists, preserving a continuous, year-by-year record of our climate's history stretching back hundreds of thousands of years. To access this archive, scientists undertake monumental drilling projects, extracting cylindrical cores of ice that are miles long. Each core is a vertical timeline, with individual layers of compacted snow representing individual years, much like the rings of a tree. Trapped within these layers are minuscule bubbles of ancient atmosphere, actual samples of the air that dinosaurs or early humans breathed. These bubbles are time capsules, preserving the precise concentration of greenhouse gases like carbon dioxide and methane from that exact moment in history. Even the dust particles frozen within the ice tell a story, revealing periods of intense drought, massive volcanic eruptions, or changes in global wind patterns. Simultaneously, on the bottom of the world's oceans, another record is being written. Fine sediments slowly rain down from the surface, accumulating in steady, undisturbed layers over millennia. These sediments are filled with the skeletons of microscopic creatures called foraminifera, the specific types of these tiny organisms that lived in a given period indicate the water temperature they thrived in. Even more remarkably, the chemistry of their shells holds a secret code. The ratio of different oxygen isotopes locked within the calcium carbonate of these fossils acts as a precise thermometer and an ice volume gauge. A higher proportion of the heavier oxygen-18 isotope generally indicates a colder climate with more water locked up in massive ice sheets, while a higher proportion of the lighter oxygen-16 suggests a warmer world with higher sea levels. By reading this isotopic code layer by layer, scientists can reconstruct not just a timeline of temperature, but of global sea level itself. By meticulously correlating the data from these ice cores and sediment layers, climatologists have built a stunningly detailed picture of our planet's past. They can pinpoint the exact timing of the great melt that ended the last ice age, an event that was supercharged by the alignment of Milankovitch cycles we discussed. The evidence shows that this wasn't a slow, gentle thaw. Around 12,000 years ago, as Earth's orientation provided more intense summer sun to the northern ice sheets, the melting entered a runaway phase. Enormous glacial lakes held back by dams of ice suddenly burst, sending catastrophic floods across continents. Sea levels did not inch upward, they surged, rising over 300 feet in a geologically brief window of time. This immense influx of water drowned entire worlds that were once home to humans. Perhaps the most famous of these lost landscapes is Doggerland, a vast, fertile plain that connected Great Britain to mainland Europe. For millennia, it was a rich hunting ground for Mesolithic peoples with rivers, hills, and forests teeming with life. Then the seas rose. The water crept across the land, swallowing valleys and forests, eventually isolating Britain as an island and erasing a complete chapter of human prehistory beneath the waves of what is now the North Sea. These natural archives provide irrefutable proof that the rewriting of our planet's coasts was not a slow, inevitable process, but a dynamic and often dramatic series of events directly tied to the celestial dance of Earth's tilt and orbit. These stories passed down through generations are far more than just entertaining folklore. They are a profound form of historical memory, echoing real and terrifying events that shaped the early human experience. Across the globe, from the Middle East to the islands of the Pacific, cultures separated by vast oceans and millennia of time all share strikingly similar narratives of a great deluge sent by displeased gods to wash away the old world. The Mesopotamian epic of Gilgamesh, one of the oldest written stories we have, describes the hero Utnapishtim being instructed by a god to build a great boat to save his family and the seeds of all living things from a world-consuming flood. On the other side of the planet, numerous Aboriginal Australian communities' Dreamtime stories tell of a time when the ancestral coasts extended far out to sea, before the ocean rose to drown their sacred sites and create the islands we see today. In the Americas, countless indigenous tribes, from the Hopi to the Maya, have their own versions of a great flood that cleansed the earth. This incredible consistency points to a shared global trauma, a collective memory of coastlines collapsing under rising waters, of communities being scattered, and of a world fundamentally and violently changed. The power of these myths becomes undeniable when we step out of the library and into the water, where archaeologists are actually finding the physical evidence of these lost worlds. Off the western coast of India, in the Gulf of Combat, marine scientists discovered the sprawling underwater ruins of an ancient city, now known as Dwarka. According to Hindu legend, this was the magnificent city of the god Krishna, a place of immense wealth and power that was said to have been swallowed by the sea upon his death. The submerged structures, pottery, and artifacts retrieved from the site date back thousands of years, providing a tantalizing link between a foundational myth and a verifiable historical settlement that now lies beneath the waves. Similarly, in Greece, the town of Pavloptri is considered the oldest known submerged city in the world, with a complete planned layout of streets, buildings, and tombs lying just off the coast of southern Laconia. This wasn't a city that slowly eroded. Evidence suggests it was fully submerged by a single seismic event linked to rising sea levels and geological instability. These are not isolated examples. From the sunken monoliths of Yonaguni in Japan to the drowned forests discovered off the coast of England, the world's continental shelves are littered with the ghostly footprints of human habitation, all dating to a period when the shoreline was miles farther out. So what connects these ancient stories to these very real, very wet ruins? The answer lies in the immense and relatively rapid rise in global sea levels that occurred as the last ice age waned. We're not talking about a gentle, incremental creep of water that gave people generations to move their homes. This was a dramatic and often terrifying reorganization of the world's geography. As massive ice sheets melted, colossal volumes of water were released. In some places, this meant a steady invasion of the shoreline, inch by inch, year after year. In other areas, the rise was catastrophic and sudden. Vast glacial lakes, held back by fragile dams of ice, would periodically burst in events known as glacial lake outburst floods. These were biblical-scale deluges, releasing torrents of water that could radically alter landscapes and sea levels in a matter of days or weeks. For the prehistoric communities living on those fertile coastal plains, some of the most resource-rich environments on the planet, this was an existential threat. They witnessed their hunting grounds vanish, their freshwater sources turn brackish, and their sacred mountains become isolated islands before finally disappearing altogether. The psychological impact of such a loss is almost unimaginable. It's no wonder that these events became seared into cultural memory, explained through the lens of divine intervention, a punishment from the gods or a necessary cleansing before a new world could be born. This intersection of geology and mythology offers us a crucial insight. While we may never find a literal, sunken continent named Atlantis exactly as Plato described it, the core truth behind the legend is very real. The stories of Atlantis, Cumri Kandam, and other lost lands are powerful metaphors for a universal human experience, the trauma of losing our home to forces beyond our control. They encode the very real history of how a wobble in Earth's axis, operating over thousands of years, could directly determine the fate of countless human societies. These myths are not mere fairy tales. They are the echoes of our ancestors who looked out at a rising ocean and struggled to make sense of the unimaginable, leaving behind a warning and a memory in the stories they told their children. But Earth's story doesn't end with coastlines simply advancing and retreating. The planet's tilt acts like a master switch, not just for ice and sea levels, but for the very engine that drives our climate, the global network of ocean currents. These currents are the planet's circulatory system, a complex web of flowing water that tirelessly redistributes heat from the equator to the poles. They are powered by two fundamental forces: temperature, which affects water density, and salinity, which is the saltiness of the water. Together, this creates the Great Conveyor Belt of the oceans, known technically as the Atlantic Meridional Overturning Circulation, or AMOC. Warm, salty surface water from the tropics flows northward like the mighty Gulf Stream, releasing its heat into the atmosphere and giving places like Ireland and England their surprisingly mild climates. As this water travels north, it cools down, becomes denser, and eventually sinks into the deep ocean, beginning a long journey back south to be reheated and start the cycle all over again. This entire delicate system is exquisitely sensitive to changes in its fuel source, the balance of temperature and salt. This is where the wobble of Earth's axis enters the picture with dramatic consequences. A shift in tilt doesn't just move the spot where sunlight is most intense, it fundamentally alters global wind patterns. Winds are the primary force that pushes surface currents along. So, a change in the wind's strength or direction can directly accelerate or put the brakes on a major current like the Gulf Stream. Furthermore, and perhaps more critically, the tilt influences how much fresh water is released from melting ice sheets. This is the system's Achilles heel. Imagine a massive pulse of cold, fresh meltwater pouring into the North Atlantic from the collapsing ice sheets of the last glacial period. This fresh water is far less dense than the cold, salty water that normally sinks there. It acts like a lid, floating on the surface and preventing the crucial sinking process from occurring. It's as if someone pulled the plug on the entire conveyor belt. When the sinking stops, the northward flow of warm tropical water slows to a crawl or even grinds to a halt. We have compelling evidence that this exact scenario has played out in the past, with breathtaking speed and devastating effect. The most famous example is a period known as the Younger Dryas, which began around 12,800 years ago. The Earth was steadily warming, emerging from the depths of the last ice age. Glaciers were retreating and seas were rising. Then, with shocking abruptness, the climate did an about-face. In a matter of decades, perhaps even less, temperatures in the North Atlantic region plummeted. Ice sheets began to advance once more, and winter-like conditions returned for over 1,000 years. The leading hypothesis for this dramatic event points directly to a colossal influx of meltwater disrupting the ocean's conveyor belt. A gigantic glacial lake known as Lake Agassiz, which was held back by an ice dam in North America, is believed to have catastrophically drained into the Atlantic Ocean. This sudden flood of fresh water effectively shut down the heat pump of the Gulf Stream. The result was a profound paradox. Even as the global climate was, on average, continuing to warm due to orbital changes, entire regions like Europe and North America were thrown back into a deep freeze. This demonstrates the incredible power of ocean currents to not just moderate climate, but to completely override larger global trends and create startling regional exceptions. The impact of these oceanic shifts rippled far beyond temperature readings. The redistribution of heat and nutrients directly dictated where life could thrive. Currents carry vital dissolved nutrients up from the deep, fueling vast blooms of phytoplankton that form the base of the marine food web. A change in a current's path could starve one fishing ground while fertilizing another, forcing entire populations of fish and the human communities that depended on them to migrate or collapse. For early societies that had settled along coastlines, a change in ocean circulation could mean the sudden disappearance of a reliable food source, or the arrival of unfamiliar and unpredictable weather patterns that destroyed their agricultural cycles. The stability of the oceans they had come to rely upon was revealed to be an illusion, a temporary calm in a system capable of violent and abrupt reorganization. This deep interconnectedness shows us that you cannot change one part of Earth's climate system in isolation. A shift in the planet's tilt, an event driven by the gravity of other celestial bodies, can trigger the melting of ice, which alters the salinity of the sea, which shuts down a current, which changes the wind and rain patterns for a continent, and ultimately determines whether a civilization flourishes or fails. It is the ultimate demonstration of Earth's complex and dynamic nature. Now, let's zoom in on one of the most compelling and controversial chapters in this story of oceanic transformation, a real-world event that reads like something from ancient mythology. Picture the Black Sea not as we know it today, a vast saltwater body, but as a much smaller, landlocked freshwater lake sitting hundreds of feet below the level of the global ocean. This was its state for thousands of years following the last ice age, a fertile oasis surrounded by higher ground, home to some of Europe's earliest farming communities. These Neolithic peoples settled along its lush shores, farming the rich soil, fishing its abundant waters, and building a life in a seemingly stable and isolated world. But far away, a global process was unfolding that would shatter their tranquility. As Earth's axial tilt continued to shift and the great ice sheets melted, the world's oceans were rising relentlessly, creeping up the narrow passage that separates Europe from Asia, what we now call the Bosporus Strait. The Mediterranean Sea was inching closer to this natural dam of rock and earth that separated it from the much lower Black Sea Lake. Then, around 7,600 years ago, the dam broke. Geologists William Ryan and Walter Pittman from Columbia University pioneered this theory, piecing together evidence that points to a cataclysm of almost unimaginable scale. They proposed that the rising Mediterranean finally overtopped the Bosporus sill, and what began as a trickle quickly became a torrent. The soft rock of the barrier would have eroded rapidly, unleashing a waterfall 200 times more powerful than Niagara Falls, thundering day and night for months, perhaps even an entire year. The sound alone would have been terrifying, echoing for hundreds of miles as a constant roar on the horizon. The salt water from the Mediterranean would have poured in with unstoppable force, gouging a massive channel as it went. The Black Sea's water level may have risen as much as 6 inches per day, swallowing up to a mile of coastline every week. For the people living there, it was a slow-motion nightmare. They would have watched their fields, their villages, and their sacred grounds disappear beneath an ever-encroaching, strangely salty tide that showed no sign of stopping until their entire world was drowned. This wasn't just a flood, it was the complete and irreversible ecological transformation of their homeland from a freshwater lake to a saltwater sea. The evidence supporting this dramatic story is etched into the seafloor itself. Sonar mapping of the Black Sea has revealed features that are unmistakable to a geologist's eye: submerged river channels and ancient shorelines far below the current water level, precisely what you would expect to find if a large landmass had been flooded. Even more conclusive data comes from sediment cores extracted from the bottom. These cores show a sharp, dramatic boundary line. Below that line, the sediments contain fossils and pollen from freshwater mollusks and plants, proof of a terrestrial or freshwater environment. But directly above that line, the sediments are suddenly filled with the saltwater shells of microscopic organisms that could only have come from the Mediterranean. This transition isn't gradual, it's geologically instantaneous, indicating a flood that was swift and catastrophic on a human timescale. The dating of this boundary aligns perfectly with the timeline of global sea level rise driven by the Earth's post-glacial axial changes, providing a powerful link between a celestial trigger and a human disaster. The cultural impact of such an event would have been seared into the collective memory of the survivors. Those who fled the rising waters would have been forced inland into Europe, Anatolia, and beyond, becoming refugees carrying with them a story of a world consumed by a vengeful sea. As this story was passed down through generations and across cultures, it could have easily evolved into the archetypal flood myth that appears in so many traditions. The parallels to the biblical story of Noah's flood are particularly striking: a catastrophic deluge sent by a higher power, a warning unheeded, and a select few surviving to repopulate the earth. While it's unlikely that any single event is the sole source for all global flood myths, the Black Sea deluge stands as a powerful and plausible candidate for one of the most enduring narratives in human history. It serves as a profound case study of how a physical change in the Earth's environment, driven by its orbital mechanics, can transcend geology to become a foundational element of culture, religion, and identity, demonstrating that the rewriting of oceans is also the rewriting of the human story. While the story of the Black Sea is one of catastrophic flooding and cultural memory, the flip side of Earth's climatic coin reveals an equally dramatic narrative: the creation and destruction of entire continents of dry land that served as highways for humanity. For tens of thousands of years, the world was a vastly different place. So much of the planet's water was locked up in colossal ice sheets that global sea levels were nearly 400 feet lower than they are today. This massive drop didn't just move the coastline, it revealed staggering expanses of the continental shelf, creating vast, habitable landscapes that are now utterly lost beneath the waves. These weren't just narrow strips of land, they were colossal bridges connecting entire continents, and they became the stage for one of the most important journeys in human history: the peopling of the Americas. The most famous of these lost worlds is Beringia. We often picture it as a simple land bridge, a narrow causeway between Siberia and Alaska. In reality, it was a massive subcontinent, over 1,000 miles wide from north to south, a vast, low-lying plain that remained unglaciated due to dry climate conditions. For millennia, this was not a bridge to be crossed quickly, but a land to be lived in. It was a frigid grassland ecosystem, what scientists call a mammoth steppe, teeming with megafauna like woolly mammoths, steppe bison, and giant elk. Early hunter-gatherer groups from Asia gradually moved into this new territory, following the herds that were their source of food, clothing, and tools. They settled there generation after generation, adapting to the cold and building a life in this unique environment. Their isolation in Beringia for thousands of years is what allowed for the distinct genetic and cultural identity of the indigenous peoples of the Americas to begin forming, long before they ever set foot on what is now the continental United States or Brazil. Then the world began to warm again. Earth's axial tilt shifted, directing more summer sunlight toward the northern ice sheets and initiating the Great Melt. This process wasn't a smooth, gentle rise. It happened in fits and starts, with rapid pulses of meltwater dramatically raising sea levels in short, catastrophic bursts. The cold, fresh water pouring into the oceans didn't just drown coastlines. It also disrupted the very ocean currents we discussed earlier, causing brief but violent returns to cold conditions that would have made life on the exposed plains incredibly challenging. For the people of Beringia, the world was literally closing in around them. The shallow seas on either side of them began to rise slowly at first, then with increasing speed. The lush grasslands they hunted were gradually inundated, replaced by the stormy, frigid waters of the Bering Sea and the Arctic Ocean. The land bridge didn't just vanish overnight, but its eventual subjugation was inevitable. By around 10,000 years ago, the connection was completely severed, and North America was isolated from Asia. The descendants of those Beringian settlers were now cut off, their path of return erased forever. This geographical isolation forced them to adapt, innovate, and diverge culturally as they spread across two entire continents, giving rise to the incredible diversity of languages, cultures, and technologies that European explorers would encounter millennia later. This same story of connection and separation played out across the globe. In Southeast Asia, a colossal expanse of land known as Sunderland connected the islands of Indonesia to the Malay Peninsula and mainland Asia. This was a huge, contiguous tropical region, likely home to rich and diverse human populations. As the seas rose, this vast continent was systematically dismembered. The Java Sea and the Gulf of Thailand flooded in, turning mountain ranges into islands and drowning river valleys. This fragmentation didn't just change the map, it created one of the most complex and biodiverse marine regions on Earth, the Indonesian archipelago, while simultaneously isolating human and animal populations on newly formed islands, driving the evolution of unique species and cultures. A similar story unfolded between Australia and Papua New Guinea, which were joined as a single landmass called Sahul. The flooding of the Torres Strait around 8,000 years ago didn't just create a new island. It cut off the indigenous peoples of Australia from thousands of years of cultural and genetic exchange with the peoples of New Guinea, leading to one of the longest continuous cultural histories in complete isolation on Earth. The crucial thing to understand is that these monumental changes were not the slow, imperceptible creep of geologic time that we often imagine. They were directly tied to the pulses and rhythms of Earth's orbital cycles, the same Milankovitch cycles that dictate the coming and going of ice ages. The melting of the ice sheets occurred in rapid surges, events now known as meltwater pulses, where sea levels could rise by several feet per decade for centuries. For a community living on a low-lying coastal plain, this would have been a terrifyingly fast transformation. A hunting ground your grandfather used could be underwater in your lifetime. A sacred mountain could become an island within a generation, and then vanish completely in the next. The Earth's wobble wasn't an abstract astronomical concept. It was a direct physical force that opened up the world for exploration and then just as decisively closed it off, guiding the paths of human migration, forcing cultural divergence, and ultimately writing the genetic and cultural map of our species as we know it today. This relentless rewriting of coastlines placed an immense and often brutal pressure on the delicate ecosystems that thrived at the boundary between land and sea. Imagine a mangrove forest, its tangled roots providing a nursery for countless fish species, suddenly finding its feet permanently underwater as the sea invades. The trees, adapted to tolerate saltwater and tidal fluctuations, have their limits. If the water rises too quickly or stays too deep for too long, the entire forest can drown, the once teeming habitat collapsing into a barren, silty graveyard. Similarly, vast coastal wetlands, crucial filtering systems for runoff and vital buffers against storm surges, faced a dire choice: either migrate inland as the waters advanced or be utterly consumed. This wasn't a peaceful transition. It was an ecological crisis forced by the planet's changing orientation, a struggle for survival dictated by the slow wobble of Earth's axis. Coral reefs, those vibrant underwater cities, faced a different but equally daunting challenge. Corals are living animals that depend on a symbiotic relationship with tiny algae called zooxanthellae, which need sunlight to photosynthesize and provide energy for their hosts. As sea levels rose, the depth of the water above the reef increased, threatening to push the corals into darker, deeper water where too little sunlight could penetrate. Their solution was a race against time, a desperate architectural feat. The coral colonies would work furiously to grow upward, building their limestone skeletons vertically to keep pace with the rising water and stay within the sunlit zone. We can see the evidence of this ancient struggle today in places like the Bahamas, where massive fossilized reef structures now stand high and dry on land. These aren't mountains in the traditional sense. They are the skeletal remains of entire ecosystems that literally built themselves upward to survive a drowning world, only to be left stranded when sea levels eventually fell again during later glacial periods. On other coastlines, the evidence of this rapid change is even more haunting. Around the world, from the North Sea to the coasts of North America, divers and scientists have discovered the remains of submerged forests. These are not logs washed out to sea. These are the intact stumps and root systems of ancient trees, still standing upright on the seafloor, preserved in the anaerobic conditions of the sediment that buried them. These ghost forests are a silent, powerful testament to a rapid inundation. They tell us that the water didn't just slowly creep in over centuries, giving the forest time to decay and fall. In many cases, it arrived with devastating speed, perhaps from a storm surge atop a higher sea level or a sudden subsidence of the land, burying the trees in sediment and saltwater before they could even rot. It's a snapshot of a moment of ecological catastrophe, frozen in time beneath the waves. The consequences for biodiversity were profound and often devastating. As sea levels rose, low-lying islands were particularly vulnerable. Isolated populations of animals that had evolved in these island sanctuaries found themselves with nowhere to run. A stark and tragic example is the case of the mammoths on Wrangel Island off the coast of Siberia. As the seas rose at the end of the last ice age, what was once a connected part of the mainland became an isolated island. A population of woolly mammoths was trapped there, while their mainland relatives went extinct due to a combination of climate change and human hunting. The Wrangel Island mammoths held on for thousands of years. However, their isolation on a shrinking landmass with limited resources led to genetic problems and eventually their demise. Their story is a direct result of the ocean's rewriting borders, creating and then destroying an isolated refuge. Yet, from this chaos, new habitats were also forged. The same rising waters that drowned forests and islands also flooded river valleys, creating new estuaries and bays with nutrient-rich waters that became hotspots for new marine life. Sandy beaches shifted inland, creating new nesting grounds for turtles and shorebirds in areas that were once inland forests. The constant change, while destructive, is also a fundamental engine of evolution and ecological renewal over these grand timescales. Scientists now study these past responses with intense interest, using them as a natural laboratory to understand how modern ecosystems might react to our current period of rapid sea level rise. By examining which species survived, which went extinct, and which ecosystems were able to migrate successfully, we can better predict which coastal environments today are most resilient and which are most at risk, drawing critical lessons from a past where the planet itself was the agent of change. This incredible detective work, piecing together stories of lost lands and shifting seas, is no longer confined to the realm of painstakingly drilling core samples or scouring ancient texts. Today, we have an entirely new arsenal of technological tools that allow us to see the ghostly outlines of these vanished worlds with breathtaking clarity. It's as if we've been given a time machine not for physical travel, but for visual reconstruction, enabling us to peel back the layers of water and time to reveal the Earth as it once was. This technological revolution is transforming our understanding of axial tilt's impact from a theoretical concept into a vividly rendered, three-dimensional reality. At the forefront of this effort is a remarkable technology called LiDAR, which stands for light detection and ranging. Imagine flying a specialized aircraft or drone over a dense, jungle-covered landscape. Instead of relying on visible light that would be blocked by the thick canopy, the LiDAR system fires hundreds of thousands of pulses of laser light per second toward the ground. These pulses penetrate the smallest gaps in the leaves and vegetation, bounce off the solid ground beneath, and return to the sensor. By precisely measuring the time it takes for each pulse to return, a computer can build an exquisitely detailed, three-dimensional map of the true ground surface, effectively digitally stripping away every tree, bush, and building. This technology has been revolutionary in archaeology, revealing entire ancient cities hidden for centuries under jungles in Cambodia and Central America. But its power is equally profound when applied to coastal areas. Scientists are now using LiDAR to map the seafloor in shallow coastal waters with incredible precision, identifying the subtle topographic signatures of drowned river valleys, ancient shorelines, and even the man-made outlines of submerged settlements that were invisible to previous sonar technologies, literally charting the lost geography created by lower sea levels. While LiDAR gives us a detailed look at specific regions, we need a global perspective to truly appreciate the scale of change, and that's where satellite altimetry comes in. This technology involves satellites equipped with highly sensitive radar that constantly measures the precise distance between the satellite and the Earth's surface. Over the oceans, this provides an incredibly detailed topographic map of the seafloor. The reason is gravity. Underwater mountains and trenches exert a slight gravitational pull on the water above them, creating subtle bulges and dips on the ocean's surface that the satellites can detect. By analyzing these surface variations, scientists can map the structures on the seafloor, revealing the sunken river systems and vast plains of continents like Sunderland and Sahel that were above water during the last glacial maximum. This global view shows us that the familiar continents we see on modern maps are merely the highest peaks of a much larger, mostly submerged continental geography, a world that was fully exposed when Earth's different tilt locked away immense volumes of water in ice. But gathering all this raw data is only the first step. The real magic happens when we feed this information into sophisticated computer models. Climate scientists and geologists use powerful supercomputers to create virtual simulations of Earth's climate system. These models don't just incorporate today's conditions, they can be programmed with the specific orbital parameters of the past, the exact calculated eccentricity, obliquity, and precession for a given date, say 18,000 years ago. When they run the simulation, the model shows how those specific axial conditions would have influenced atmospheric circulation, precipitation patterns, and most critically, the growth and melt of ice sheets. The output is a dynamic, visual representation of how coastlines changed over centuries, showing the dramatic flooding of regions like the Persian Gulf, which was not always a salty inlet. Just 8,000 years ago, this area was a fertile river valley known as the Gulf Oasis, watered by the extended courses of the Tigris and Euphrates rivers and home to rich human settlements. The models show with startling clarity how the rising seas from the melting glaciers eventually breached the narrow Strait of Hormuz, transforming this verdant landscape into the oceanic basin we see today. Perhaps the most startling revelation from this high-tech toolbox is the proof that these processes are not locked in the deep past. They are actively happening right now. NASA Gravity Recovery and Climate Experiment, or GRACE, satellites have been meticulously measuring tiny changes in Earth's gravitational field for decades. Their data has unequivocally shown that the massive melting of the Greenland and Antarctic ice sheets, driven by modern human-induced global warming, is redistributing enough weight on the planet's surface to cause a measurable shift in the tilt of Earth's axis. The principle is straightforward. A spinning object's axis will wobble if its mass is redistributed. As billions of tons of ice melt from the poles and that water spreads across the global ocean, the planet's balance is altered, and its axis literally moves in response. This provides a direct and undeniable link between contemporary climate change and the same fundamental planetary processes that drove the sea level changes of the past, proving that the great rewriting of oceanic borders is a continuous story, and we are now active participants in its next chapter. This profound reshaping of coastlines did far more than redraw maps. It actively rewrote the very script of human civilization, elevating some societies while utterly erasing others from history. Consider the fate of communities whose entire existence was anchored to the shoreline. For generations, these coastal cultures thrived, their lives and economies built upon the rich bounty of the sea and the strategic advantage of maritime trade routes. But when the oceans began their relentless advance, these same advantages became their greatest vulnerabilities. A thriving port city could find its harbor silting up and its protective reefs drowned within a few generations, its connection to the wider world severed as the sea transformed its waterfront into a swampy, inaccessible bog. The very source of their wealth and power became the instrument of their decline, forcing a painful choice between a desperate, costly fight against the water or a full retreat inland, often into territories already occupied by rivals. We see this dramatic power shift etched into the archaeological record of the ancient Mediterranean. The Minoan civilization on Crete, renowned for its stunning palaces, vibrant art, and vast maritime trade network, is a classic example of a coastal power brought low by a confluence of environmental disasters. Their sophisticated society was heavily dependent on the sea, not just for trade but for sustenance. A massive volcanic eruption on the island of Thera, now known as Santorini, occurred around 1600 BCE, an event that was likely amplified by the higher sea levels of the time. The eruption itself was catastrophic, but it was the tsunamis that followed that may have delivered the crippling blow to Minoan port cities and coastal infrastructure. While the exact sequence of their decline is complex, involving possible invasion and internal strife, there is little doubt that this environmental catastrophe, supercharged by the changing seas, severely weakened their maritime dominance. This created a power vacuum that was swiftly filled by the more inland, militaristic Mycenaeans from the Greek mainland, who went on to dominate the region and lay the groundwork for classical Greece. The Minoan story is a powerful lesson in how a society's greatest strength can become its ultimate Achilles heel when the planet decides to rewrite the rules. Far from the Mediterranean, Another great ancient civilization found its fortunes inextricably tied to the whims of a climate system influenced by these grand planetary cycles. The mighty Egyptian empire was in essence a gift of the Nile River. Its annual, predictable flood cycle deposited rich, life-giving silt across the floodplain, creating the agricultural surplus that supported pharaohs, pyramids, and a complex society for millennia. But ancient records, such as inscriptions on tomb walls and papyrus scrolls, speak of periods of chaos and despair, times when the Nile failed. There were years of famine so severe that they triggered social unrest, the collapse of central authority, and even the fall of dynasties. Modern climate science, using proxy data from cave formations and lake sediments, suggests that these periods of low Nile floods often coincided with broader global climate shifts. A change in the intensity of monsoon rains over the Ethiopian highlands, the source of the Nile's water, could be triggered by the same axial and orbital variations that were melting ice sheets elsewhere. A slight shift in the planet's tilt could alter atmospheric circulation patterns, diverting the rains that fed the Nile, and in doing so, threatening the very heart of Egyptian power. The pharaohs may have been seen as living gods, but their authority was ultimately subject to the same cosmic clock that governed the entire planet. The ripple effects of these oceanic and climatic changes extended far beyond the collapse of single empires. They fundamentally redirected the flow of global interaction. The slow, inevitable drowning of low-lying coastal plains didn't just destroy individual settlements. It erased entire geographic shortcuts and created formidable new barriers. The flooding of land bridges, as we've discussed, isolated populations, but it also forced the invention of new technologies and the exploration of new paths. When direct overland routes were cut off by rising waters, societies were compelled to look to the sea with new ambition, spurring advancements in boat building and navigation. The need to traverse newly formed bodies of water may have been a key driver behind the incredible seafaring prowess of cultures like the Phoenicians, who became the master traders of the ancient world not by choice, but by necessity, their fortunes literally riding on the waves of a changed world. This redrawing of the map dictated the paths of conquest, the spread of ideas, the exchange of technologies, and the very pattern of cultural diffusion that defines our shared history. It reminds us that the silent, slow-motion dance of Earth's axis is not just a background process. It is a silent, powerful character in the human story, an unseen force that has toppled kings, scattered populations, and sparked revolutions, proving that our history is and always has been a dialogue with our dynamic planet. The disappearance of Earth's most magnificent giants stands as one of the most haunting puzzles in our planet's history. For millions of years, creatures of astonishing scale roamed the continents, woolly mammoths with tusks curving like ancient tree trunks, saber-toothed tigers armed with daggers for teeth, and giant ground sloths that stood as tall as houses. Then, in a geological blink of an eye, they were gone. The timeline of their vanishing act is uncanny. It coincides almost perfectly with two world-altering events: a dramatic rise in global sea levels and the expansion of human hunters across the globe. This wasn't a slow fading away. It was a relatively abrupt collapse of entire megafaunal communities, and the key to understanding it lies in the profound environmental chaos unleashed by Earth's shifting axis. When we picture the world these giants called home, we must imagine a landscape utterly foreign to us today. During the peak of the last ice age, much of the northern hemisphere was covered in a vast, cold, and dry grassland ecosystem known as the Mammoth Steppe. This was not a barren wasteland. It was an incredibly productive environment, a sea of grasses and herbs that stretched from Spain across Eurasia and over the Bering Land Bridge into North America. This ecosystem was perfectly suited to support massive herds of mega herbivores. The woolly mammoth, the woolly rhinoceros, and the giant bison were not just living on this steppe, they were essential to its maintenance. Their grazing kept woody shrubs and trees at bay, their trampling compacted the soil, and their fertilizing dung nourished the grasses, creating a self-sustaining environment that could support an incredible biomass of large animals. This was their world, stable and thriving for millennia. Then the clockwork of the Milankovitch cycles turned. Earth's axial tilt began to shift, directing more summer sunlight toward the northern ice sheets. The Great Melt began, and the world started to change at a pace that these colossal creatures simply could not match. The first major blow was the transformation of their habitat. As the climate warmed and became wetter, the composition of the vegetation began to shift. The dry, nutrient-rich grasslands that the megafauna depended upon were gradually invaded by mosses, then by shrubs, and finally by forests. A mammoth or a rhino built to digest grasses is poorly equipped to survive in a dense, woody swamp or a closed canopy forest. Their primary food source was literally disappearing beneath their feet, replaced by ecosystems that offered them little sustenance. Furthermore, the rising seas we've been discussing played a devastating role in fragmenting this once continuous world. The mammoth steppe was an interconnected continent-spanning biome, allowing for genetic exchange and seasonal migration. As the oceans rose, they drowned the most crucial connections, particularly the Bering Land Bridge. This act of geographic separation trapped populations on shrinking islands of habitat, like the mammoths on Rangel Island or the St. Paul Island mammoths in Alaska. Isolated and cut off from larger populations, these groups became vulnerable to inbreeding, disease, and local resource scarcity. A bad season or a single epidemic could wipe out an entire isolated population for good. Into this world of increasing climatic stress came a new and potent predator: humans. Homo sapiens, with their sophisticated hunting tools, cooperative strategies, and relentless expansion, emerged from Africa and spread across the continents right as this environmental upheaval was reaching its peak. The debate between scientists who favor climate change as the primary driver of the extinctions and those who point the finger at human overhunting, often called the Blitzkrieg hypothesis, is one of the great scientific detective stories. The truth likely lies in a deadly combination of both factors. A healthy, stable population of mammoths might have withstood the pressure from a new predator. But a population already stressed by habitat loss, nutritional decline, and geographic isolation was incredibly vulnerable. Humans did not need to hunt every last mammoth. They merely needed to be the final, persistent pressure on a system that was already collapsing from within. Evidence from archaeological sites shows that humans did indeed hunt these giants, and cave paintings from Lascaux to Altamira testify to the deep cultural impression these animals left on our ancestors. The disappearance of land bridges also meant that these giant animals, trapped on continents like North America, had nowhere to flee from the advancing human populations. The evidence for this multifaceted catastrophe is preserved in some of the coldest places on Earth. In the Siberian and Alaskan permafrost, scientists have unearthed a treasure trove of frozen megafauna, from perfectly preserved baby mammoths with their last meal of grasses still in their stomachs to the carcasses of steppe bison. These frozen time capsules provide direct physical proof of the animal's diet and the rapidity of their burial, often in conditions suggesting sudden climate shifts like flash floods or mudslides. The layers of ice cores themselves tell the parallel story of the atmosphere changing, with rising greenhouse gas levels and shifting temperatures that correlate perfectly with the extinction horizon. This convergence of evidence paints a heartbreaking picture of a world turning upside down. The very planetary forces that had created the perfect home for these giants, the specific axial tilt that maintained the Ice Age, began to shift, dismantling that world piece by piece. The giants of the Earth, who had survived countless cycles of change before, found themselves caught in a perfect storm of habitat fragmentation, nutritional stress, and a clever new adversary. Their extinction is a powerful reminder that no species, no matter how large or well adapted, is an island. We are all deeply embedded in and dependent upon the stability of our environment. And when the fundamental rules of that environment are rewritten by the slow wobble of a planet in space, the consequences can be truly monumental. While the frozen tombs of the tundra preserve the remains of megafauna, another type of time capsule lies hidden in the dark, silent world beneath the waves, holding secrets not of extinct animals but of our own ancestors. The relentless rise of the oceans, driven by Earth's shifting tilt, did not merely drown landscapes, it entombed them. In the deep, cold, and oxygen-poor conditions of the seafloor, a remarkable process of preservation takes place. The absence of oxygen, known as an anaerobic environment, dramatically slows decay. Wood, bone, plant material, and even woven fabrics that would have completely rotted away on land can survive for millennia, perfectly conserved in the mud and silt. These are not just scattered artifacts, these are entire snapshots of prehistoric life, frozen in time at the very moment the waters closed over them, waiting for us to rediscover the lost chapters of human history they contain. Some of these underwater discoveries ignite the imagination and spark fierce debate, challenging our understanding of ancient human capabilities. Off the southern coast of Japan, near Yonaguni Island, divers explore a massive, enigmatic structure known as the Yonaguni Monument. This sprawling formation features what appear to be massive, geometric terraces, straight walls, and even staircases carved into the bedrock. The sheer scale and seemingly architectural precision of the site have led some researchers to propose it is the remnant of a lost, advanced civilization, perhaps a Japanese counterpart to Atlantis, submerged by rising seas thousands of years ago. Mainstream geologists, however, argue compellingly that the monument is a spectacular but entirely natural formation, created by tectonic activity and the powerful underwater currents that have eroded the sandstone into sharp, geometric planes. Similarly, in the Baltic Sea, sonar images revealed a highly unusual, circular anomaly resting on the seabed, its strange shape instantly fueling speculation about a sunken UFO or a mysterious ancient structure. Further investigation suggested it was most likely a glacial deposit, but the initial mystery captivated the world, demonstrating our deep fascination with the idea of lost worlds hidden beneath the waves. Yet for every controversial anomaly, there are countless other sites that provide unambiguous, breathtaking evidence of human habitation. Along the coast of Israel, for instance, lies the submerged Neolithic village of Atlat Yam. This settlement, dating back over 9,000 years, was discovered under roughly 30 feet of water, preserved with an almost miraculous level of detail. Archaeologists mapping the site have found the stone foundations of houses, a circular arrangement of massive stones that appears to be a ritual site, and even a freshwater well, now filled with seawater. Most poignantly, they uncovered human burials, including the skeletons of a woman and child, offering a silent, somber connection to the people who lived, worked, and died in this place when it was dry land. The preservation is so exceptional that analysis of the skeletons even revealed evidence of tuberculosis, pushing back the known history of this disease by thousands of years. This isn't just a collection of old stones, it is a ghost town, a complete community that was abandoned as the Mediterranean Sea inexorably encroached upon their homes, providing an incredibly rare window into the daily life of some of the world's earliest farmers. Each of these sunken sites, from the debated to the definitive, adds a crucial piece to the vast puzzle of our past. They force us to radically recalibrate our maps of ancient human migration and settlement. For decades, archaeologists primarily looked inland along river valleys and known trade routes to trace the spread of humanity. The discovery of sophisticated settlements on what were once coastal plains now underwater suggests a completely different narrative. It implies that some of the most advanced and populous communities of the prehistoric world may have thrived along shorelines that are now completely lost to us. These were likely ideal locations, offering a rich mix of resources from both the land and the sea. The rising oceans didn't just force people to move, they systematically erased the very evidence of where some of the most innovative and adaptable human societies had once flourished. Every time a dive team discovers a new submerged village or a carefully crafted tool on the continental shelf, it rewrites a sentence in our history books, proving that early humans were not just passive victims of climate change, but were often thriving in the very areas most vulnerable to the planet's shifts. The story these underwater treasures tell is ultimately one of profound human resilience and adaptation in the face of planetary transformation. The people of Atlantis did not simply vanish when the waters began to rise. Evidence suggests they tried to adapt, perhaps building simple barriers or raising their floors, before finally conceding to the ocean's power and migrating inland. This pattern likely played out countless times across the globe, from the North Sea to the coasts of Australia. Each flooded settlement represents a community that was forced to innovate, to change their way of life, or to embark on a perilous journey into unknown territories. This constant pressure from a changing environment may have been a critical catalyst for human development, forcing the sharing of technologies, the exploration of new lands, and the development of more complex social structures to deal with the crisis. The archaeological treasures beneath the waves are more than just relics. They are monuments to human ingenuity, reminding us that our species' history has always been a dynamic dance with a dynamic planet, a story of learning to survive and ultimately thrive even as the very ground beneath our feet was literally washed away. This concept of interconnected change brings us to one of the most crucial and powerful ideas in climate science, the feedback loop. When we talk about Earth's axial tilt rewriting the world, we're not describing a simple, linear process where a little more tilt directly leads to a little more melt. Instead, it's more like pushing the first domino in an incredibly long and complex chain reaction. A small nudge from the planet's orientation can initiate self-reinforcing cycles that dramatically amplify the initial change, often pushing the climate system past a point of no return and unleashing transformations that are both massive and, on human timescales, virtually irreversible. Perhaps the most visually straightforward of these amplifiers is the ice albedo feedback loop. Albedo is simply a scientific term for reflectivity. Fresh, white snow and ice have a very high albedo, meaning they act like a giant mirror, reflecting a tremendous amount of the sun's energy back out into space and helping to keep the planet cool. Now imagine a period where Earth's tilt increases, delivering more intense summer sunlight to the polar regions. This warmth begins to melt the edges of the great ice sheets. But as the ice retreats, it doesn't just add water to the ocean. It reveals the much darker land or ocean underneath. Dark surfaces, whether rocky ground or deep blue seawater, have a very low albedo. Instead of reflecting sunlight, they absorb it, trapping the heat and warming the immediate environment. This local warming then accelerates the melting of the adjacent ice, which exposes even more dark surface, which absorbs even more heat, leading to even more melting. It's a vicious cycle of self-destruction for the ice sheets. This single feedback loop is believed to have been a primary engine behind the rapid pulses of meltwater that caused sea levels to soar in fits and starts, rather than in a smooth, predictable line. Once this cycle kicked into high gear, the melting could continue to accelerate even if the initial orbital conditions remained constant, demonstrating how these systems can take on a life of their own. Beneath the ocean's surface, another potent feedback mechanism lies in wait, one that involves a greenhouse gas far more powerful than carbon dioxide. Trapped within the cold, pressurized sediments of the continental shelves are vast reservoirs of frozen methane, a substance known as methane clathrate. For millennia, these deposits have remained stable, locked away by the cold, deep water above them. However, when large-scale changes in Earth's climate disrupt the ocean's circulatory system, this stability can be shattered. As we've seen, a shift in tilt can alter wind patterns and melt ice, sending pulses of fresh water into the oceans that can disrupt currents. If a change in circulation brings warmer water into contact with these frozen seabed reservoirs, it can destabilize them, triggering the release of methane bubbles that rise through the water column and erupt into the atmosphere. Methane is an incredibly potent heat-trapping gas, over 80 times more effective at warming the planet than carbon dioxide over a 20-year period. A large-scale release could therefore cause a sharp, sudden spike in global temperatures. This warming would then further disrupt ocean currents and melt more ice, potentially destabilizing even more clathrate deposits and releasing more methane. This terrifying scenario, often called the clathrate gun hypothesis, is a prime example of a feedback loop that could push the climate system into a radically different state extremely quickly, turning a gradual change into a runaway catastrophe. The critical lesson from studying these ancient loops is the concept of tipping points. Earth's climate system doesn't always respond to pressure in a gentle, predictable way. Think of it more like leaning on a canoe. You can tilt it a little and it will rock but then return to level. But if you lean just a bit too far past a certain angle, the canoe will flip over completely. That point of no return is the tipping point. The feedback loops are the weight that helps push it over. The evidence from past periods of axial shift suggests that our planet has several of these climatic tipping points. Once a threshold is crossed, like the amount of ice loss needed to seriously weaken the ocean conveyor belt, or the ocean temperature required to trigger large-scale methane release, the resulting change becomes self-sustaining and incredibly difficult to stop. The system will then drive itself toward a new equilibrium, whether we like it or not. This is how a variation in Earth's tilt of just a degree or two could orchestrate the drowning of entire continents. It wasn't the direct cause, but it was the initial push that started the chain reaction, toppling the first domino that then triggered an unstoppable cascade. This deep time perspective transforms the ancient story of axial tilts and rising seas from a fascinating historical mystery into a crucial warning for our modern world. While the natural cycles of Milankovitch would currently be pointing us toward a very gradual cooling trend, human activities have overridden this natural signal. By burning fossil fuels and pumping enormous quantities of greenhouse gases into the atmosphere, we are effectively simulating the warming effects of a drastic axial tilt change, but at a pace that is hundreds of times faster than anything nature has produced in millions of years. We are now the ones pushing on the climate system, and we are dangerously close to activating the very same feedback loops and tipping points that created such chaos in the past. The rapid melting of Arctic sea ice and the Greenland ice sheet is a stark demonstration of the ice albedo effect in action right now. Concerns about the stability of methane deposits on the Arctic seabed are a direct echo of the clathrate gun hypothesis. Understanding these ancient mechanisms allows us to see our current situation not as a novel, unpredictable event, but as a grand and terrifying experiment we are running on the planet's most sensitive and powerful systems. The past shows us the incredible force of these feedback loops once they are unleashed, and it underscores the urgent need to stop pushing the system before it pushes back in ways we can no longer control. This incredible intersection of ancient story and hard science reveals a profound truth about human nature. We are a species of meaning makers. When confronted with events so vast and terrifying they defy simple explanation, we weave narratives to contain the trauma, to pass a warning down through generations, and to find some semblance of order in the chaos. The global consistency of flood myths isn't a coincidence. It's a collective memory, an echo of a time when the very foundations of the world seemed to crumble beneath the waves. These stories, from the Epic of Gilgamesh in Mesopotamia to the Dreamtime tales of Australia's first peoples, share a common core, a deluge of divine origin that cleanses the world of its old ways, sparing only a righteous few to begin anew. For centuries, these accounts were often dismissed by scholars as purely symbolic, powerful metaphors for spiritual renewal, but lacking a basis in physical reality. The discovery of actual, physical ruins lying on the seafloor, however, forces us to reconsider. It suggests that these myths are not just allegory, but are rooted in a deep, shared experience of catastrophic loss. Take the ancient city of Dwarka, a cornerstone of Hindu tradition. The sacred texts describe it in lavish detail, a magnificent city of gold and silver, founded by the god Krishna, a beacon of power and prosperity. The legends recount that upon Krishna's departure from the earthly realm, the entire city was swallowed by the sea, lost in a single day and night. For millennia, this was understood as a theological story, a tale of a divine era coming to a close. Then, marine archaeologists began exploring the waters off the modern coast of Dwarka. What they found was stunning, massive stone structures, ancient harbor works, and a wealth of artifacts lying in up to 100 feet of water. Pottery recovered from the site has been dated to match the traditional time frame of the city's legendary submergence. While the discoveries may not confirm the divine details, they powerfully corroborate the core historical event. A thriving coastal settlement was indeed consumed by the rising sea, an event so traumatic it became immortalized in scripture. The myth, it seems, preserved the memory of a real geological catastrophe. On the other side of the world, the indigenous cultures of Australia hold some of the oldest continuous oral histories on the planet. Their Dreamtime stories are not merely tales, they are a complex map of lore, identity, and connection to the land. Woven through these narratives are consistent accounts of coastlines that once stretched far out to sea, of hunting grounds that are now underwater, and of a time when islands like Tasmania were connected to the mainland. For example, stories from the Gunditjmara people of Victoria describe the eruption of the Budgebim volcano, an event geologists have now dated to over 30,000 years ago. Similarly, numerous stories from northern Australia detail the flooding of the continental shelf, describing the ocean pouring into low-lying basins and drowning the old world. The precise details of these oral histories, passed down for hundreds of generations without a written language, align astonishingly well with our scientific understanding of post-glacial sea level rise. These aren't vague recollections, they are specific, place-based memories of a changing landscape, a testament to the power of oral tradition to act as a historical archive. The timing of these events is the final, crucial piece of the puzzle. geologists have identified several periods of extremely rapid sea level rise, known as meltwater pulses, which occurred as the last ice age waned. The most significant of these, meltwater pulse 1A, happened approximately 14,000 years ago. During this event, global sea levels are estimated to have risen by over 60 feet in less than 500 years. That's an average of over a foot per decade, a rate that would be terrifyingly obvious within a single human lifetime. Imagine watching the ocean claim a mile of your ancestral homeland within your own lifetime, with no understanding of why it was happening. For prehistoric coastal communities, this wasn't a slow geological process. It was a visible, relentless, and existential threat. The psychological impact would have been immense, creating a trauma that demanded an explanation. Lacking the concepts of glacial cycles or axial precession, the only framework available was the supernatural, the actions of gods or ancestral spirits. The flood myth, in all its variations, was the inevitable human response to an incomprehensible natural disaster. This beautiful convergence of mythology and geology does not diminish the power of the stories, it enriches them. It shows us that our ancestors were astute observers of their world. They witnessed real events and sought to explain them using the tools they had: narrative, metaphor, and spirituality. The story of a great flood sent by a displeased god is not a primitive fairy tale. It is a sophisticated cultural mechanism for processing and surviving environmental trauma. It allowed communities to make sense of the inexplicable, to assign meaning to loss, and to forge a new identity in a radically altered world. This intersection reminds us that science and storytelling are not opposing forces, but are two complementary ways of seeking truth. One relies on data extracted from ice cores and sediment layers, the other on wisdom preserved in ritual and verse. Together, they provide a more complete, more human picture of our past, revealing how the slow wobble of a planet in space could resonate so deeply that its echo would still be heard in our oldest stories today. So where does this leave us today in an age of satellites and supercomputers? The grand, slow-motion dance of Earth's axial tilt continues its stately pace as it has for billions of years. Currently, our planet's obliquity is in a very gradual phase of decrease, a tiny shift that, if left to nature alone, would nudge us towards slightly milder seasonal contrasts over the next 10,000 years. But a powerful new force has entered the equation, one that operates not on a geological timescale but on a human one. Our relentless emission of greenhouse gases from burning fossil fuels is artificially superheating the planet, dramatically accelerating processes that are normally the exclusive domain of Milankovich's celestial clockwork. We are, in effect, giving the Earth's climate system a massive and unprecedented shove, mimicking the warming effects of an extreme axial shift, but at a velocity that is hundreds of times faster than anything in the natural record. The consequences of this human intervention are already physically altering the planet's orientation in space. NASA's meticulous satellite observations, particularly from the GRACE and GRACE-FO missions, have detected a measurable shift in the distribution of the Earth's mass. As trillions of tons of ice melt from the Greenland and Antarctic ice sheets, that weight is redistributed as water flows into the global ocean. This massive movement of mass is enough to unbalance the planet's spin, much like a figure skater extending their arms to slow their rotation. This phenomenon, known as polar drift, is a direct and startling confirmation that human activity is not just warming the atmosphere, but is tangibly changing the Earth's fundamental geophysics. The axis upon which our world turns is literally moving in response to what we have done. This acceleration of natural cycles places us on the precipice of a future that we have, ironically, already seen before but never at this speed. The ancient evidence we've explored, from the drowned forests to the submerged cities, provides us with a sobering preview of what is to come. The same feedback loops that rapidly flooded Doggerland and Beringia are now being activated anew. The ice albedo effect is in full swing in the Arctic, where dark, open ocean absorbs more heat than reflective ice, leading to even more melting. The potential destabilization of methane clathrates on the seafloor remains a terrifying wild card. By studying these past events, we can forecast with chilling clarity the cascading impacts, not just a slow, incremental creep of the seas, but more frequent and catastrophic coastal flooding, the intensification of storms as they draw energy from warmer ocean waters, and the eventual displacement of hundreds of millions of people who live in low-lying communities from Miami to Mumbai, Shanghai to the Nile Delta. Yet this time there is a critical and profound difference. Our ancestors who witnessed the ocean reclaim their world had no understanding of the planetary forces arrayed against them. They could only interpret the rising waters as the capricious wrath of gods and respond with myth and migration. We, however, are blessed with the curse of knowledge. We possess a detailed playbook of the past and sophisticated models that project the future. This awareness comes with an immense responsibility. We are the first generation to see this crisis coming with such clarity, and the last generation that can take meaningful action to mitigate its most extreme outcomes. The knowledge of ancient axial shifts and their power is no longer just a fascinating historical mystery. It is an urgent call to action. It underscores the absolute necessity of a global transition away from carbon-intensive energy sources, the development of resilient coastal infrastructure, and the protection of natural barriers like wetlands and mangroves that can absorb the ocean's energy. We are living in our own era of oceanic rewriting, but unlike our ancestors, we have the tools, the technology, and the forewarning to steer its course. The question is no longer if the borders will change, but how we will choose to adapt to that new world. While Earth's axial tilt sets the stage for global climate shifts, it is far from the only actor in this planetary drama. Deep beneath our feet, another set of powerful forces is constantly at work: the restless energy of volcanism and the slow, monumental grinding of tectonic plates. These internal processes don't just operate on a separate track. They engage in a complex and often devastating dance with the climatic changes driven by our planet's wobble, amplifying effects and creating catastrophes that can rewrite coastlines in a single, violent day. Imagine the strain of a world adjusting to a new balance. As massive ice sheets melted due to axial shifts, an enormous weight was lifted from the continents. This process, known as glacial isostatic adjustment, is like pressing your thumb into a ball of dough and then releasing it. The land, once compressed by miles-thick ice, begins to slowly rebound upward. But this rebound isn't uniform. It can trigger immense geological stress, potentially increasing volcanic activity as the Earth's crust finds a new equilibrium and possibly awakening dormant fault lines, leading to more frequent and powerful earthquakes. This means that during periods of significant axial change, coastal communities weren't just facing a gradually rising ocean. They were also living on a planet that was literally shuddering beneath them. The link between these climatic shifts and Earth's fiery interior is more than just theoretical. Major volcanic eruptions inject colossal quantities of ash and sulfur dioxide high into the stratosphere, where they can form a lingering veil that reflects sunlight back into space. This can cause short-term global cooling periods that temporarily counteract the warming from a tilt shift, adding another layer of complexity to the climate record. Conversely, prolonged periods of extensive volcanism can release vast amounts of carbon dioxide, a potent greenhouse gas that can contribute to long-term warming. It's a climatic pendulum swing driven from deep below, capable of either masking or magnifying the effects of our planet's orbital journey. Tectonic activity adds another direct and physical dimension to the reshaping of coastlines. While the global sea level might be rising due to meltwater, local sea level is also dramatically affected by whether the land itself is rising or sinking. In regions where tectonic plates are colliding, land can be thrust upward, seemingly pushing the sea back. In other areas, like river deltas where sediment is compacting or where tectonic plates are pulling apart, the land can be subsiding, causing the local sea level to rise much faster than the global average. This means that for many ancient communities, their fate was sealed not just by the water coming toward them, but by the very ground disappearing beneath their feet. Perhaps no single event better illustrates this deadly synergy than the Storegga slide. Around 8,200 years ago, a truly catastrophic geological event occurred off the coast of Norway. An enormous section of the continental shelf, a slab of sediment over 200 miles long and several thousand cubic miles in volume, suddenly and without warning broke away and slid into the deep abyss of the Norwegian Sea. The scale is almost impossible to comprehend. It was one of the largest underwater landslides ever discovered. The immediate cause is still debated. It could have been triggered by a tectonic tremor, itself possibly related to the stresses of post-glacial rebound. Another compelling hypothesis points to the release of methane hydrates. These are frozen, ice-like deposits of methane gas trapped within the sediment on the seafloor. As the ocean warmed in the post-Ice Age world, a warming driven by those axial changes, these deposits may have destabilized, turning from solid to gas, building up pressure until they explosively shattered the sediment holding them, liquefying the entire slope and triggering the collapse. The consequences were apocalyptic. The sudden displacement of such a colossal volume of water generated a mega tsunami of unimaginable power. Wave models suggest that the initial wave may have been as high as a modern skyscraper out at sea. As it radiated across the North Atlantic, it would have reached the coastlines of Norway, Iceland, and Greenland with devastating force. But it was the wave's impact on the low-lying plains of what is now the North Sea that created a perfect storm of disaster. This region, including the inhabited landmass known as Doggerland, was already experiencing relentless sea level rise from glacial melt. The land was slowly drowning, its communities gradually adapting to the encroaching waters. Then, in a matter of hours, the Storegga tsunami arrived. A wall of water, possibly over 30 feet high, would have swept across these vulnerable, flat plains, scouring the landscape, drowning everything in its path, and delivering a killing blow to a civilization already under siege by the ocean. Archaeological evidence from the seabed, including scattered animal bones and primitive tools, suggests that human hunter-gatherers were present in Doggerland at this time, and the tsunami would have been a cataclysmic event that reshaped their world in an instant. This convergence of events, axial tilt warming the seas, which destabilizes geological formations, which then fail and trigger a tsunami that floods a coast already sinking from rising seas, is the ultimate example of Earth systems interconnecting. It shows us that we cannot view planetary change through a single lens. The story of our oceans is not just one of astronomy or climatology or geology. It is a story woven from all these threads simultaneously. A slight change in our planet's orientation in space can, through a cascade of effects, ultimately trigger a geological catastrophe that wipes entire landscapes off the map. This complex interplay creates profound puzzles for scientists, as they must untangle the clues left behind to determine whether a submerged forest was drowned by steady sea level rise or a single tsunami. or whether a layer of ash in an ice core came from a volcano awakened by the melting of ice. It reveals a world of breathtaking dynamism where the tilt of the axis, the fury of volcanoes, and the shift of tectonic plates all collaborate in an endless, powerful dance to rewrite the borders of our world. This pivotal moment in human history, the dawn of agriculture, did not occur in a stable, predictable world. Instead, it was born from a period of profound environmental upheaval, a direct consequence of Earth's changing tilt and the great melt that followed. For thousands of years, many human societies had thrived as highly mobile hunter-gatherers, their lives intricately tuned to the seasonal migrations of game and the abundant, diverse resources found along the world's coastlines. These coastal plains were the supermarkets of the prehistoric world, offering a rich and relatively reliable mix of seafood, birds, and lush vegetation. But as the planet warmed and the oceans began their relentless advance, these incredibly productive zones started to vanish beneath the waves. The loss was not gradual over millennia. It was a crisis that unfolded over generations, a visible and terrifying encroachment that forced communities into a corner. They could not simply follow the coastline inland because the water was following them, relentlessly consuming their ancestral hunting and gathering grounds. This immense environmental pressure created a powerful incentive to innovate, to find new ways of securing food from a landscape that was shrinking before their eyes. In regions like the Fertile Crescent, an arc of land cradled by the Tigris and Euphrates rivers, this pressure may have been the crucial catalyst, as rising seas and a warmer, wetter climate pushed populations inland. They found themselves concentrated in river valleys and upland areas. These environments were different from the open coasts. They supported wild stands of cereal grasses like wheat and barley, and were home to animals like goats, sheep, and cattle that could be managed. The concentration of people and resources in these smaller areas, combined with the urgent need to replace lost coastal food sources, likely accelerated experiments with these plants and animals. It was no longer enough to simply harvest wild grains. People began to selectively sow the seeds of the best plants, clearing land and protecting their crops. They started to corral and manage herds, ensuring a readily available supply of meat, milk, and hides rather than relying solely on the uncertain pursuit of wild game. This shift from foraging to farming was a revolution in slow motion, a series of desperate adaptations that eventually unlocked an entirely new way of life, one that allowed for permanent settlements, population growth, and the accumulation of surplus resources. Yet, while some communities were being squeezed by the rising waters, others found themselves presented with astonishing new opportunities carved from the aftermath of the ice. In vast northern regions once buried under unimaginable weights of glaciers, a different process was unfolding. As the ice retreated, the land itself, freed from its crushing burden, began to slowly rebound upward in a process known as isostatic uplift. This rising land, combined with the lower sea levels that still persisted in some areas immediately after the glacial maximum, exposed entirely new territories. These were not barren wastelands. They were lands of incredible fertility, covered in rich sediments that had been ground down and deposited by the glaciers themselves. The draining of shallow seabeds and the emergence of these new plains created verdant, open landscapes perfect for grazing animals and, eventually, for cultivation. Furthermore, the stabilization of the climate following the major axial adjustments provided something hunter-gatherers turned farmers desperately needed: predictability. The wild swings between extreme cold and warmth began to settle into more reliable seasonal patterns, allowing for the first time to plan an agricultural calendar, to anticipate rains, and to expect a harvest. This newfound climatic stability was the essential foundation upon which the gamble of farming could finally pay off, turning a risky experiment into a sustainable strategy for survival. The domestication of plants and animals, therefore, was not a single brilliant invention but a fragmented, global response to a planet in flux. In the hills of the Fertile Crescent, it was wheat and barley. In China, it was rice and millet along the river valleys. In the Americas, it was maize and squash. In each of these cradles of civilization, the story was similar but unique: local peoples responding to local environmental changes, many of which were ultimately orchestrated by the grand-scale rewriting of the world's climate and coasts. The incredible diversity of agricultural foundations around the globe points to a universal truth: humanity's greatest cultural leap was not a triumph over nature, but a deep and intricate adaptation to its rhythms. The Earth's axial behavior by melting ice and flooding coasts didn't just destroy our old way of life, it actively created the conditions that made a new one not only possible but necessary. This demonstrates that the most powerful forces of cultural change are often not kings or conquests, but the silent, slow-motion tilts of a planet that constantly challenges its inhabitants to adapt, innovate, and ultimately to evolve. While Earth's axial tilt plays the lead role in our planet's long-term climate story, it doesn't perform alone. It's part of a cosmic ensemble where other astronomical forces occasionally step into the spotlight, adding complexity and sometimes drama to the narrative of how our world changes. The Sun itself is not a constant, unwavering beacon. It goes through cycles of activity, with its magnetic field and sunspot numbers ebbing and flowing over an 11-year period. These changes cause slight variations in the solar irradiance that reaches Earth, a tiny but measurable fluctuation that can nudge our climate system. During periods of low solar activity, such as the famous Maunder minimum in the 17th century, Europe and North America experienced a pronounced cold snap known as the Little Ice Age, a time when frost fairs were held on the frozen River Thames. While this solar influence is real, its overall impact is significantly smaller than the powerful, rhythmic changes orchestrated by Earth's orbital cycles. Another intriguing cosmic player is the flux of high-energy particles from deep space known as cosmic rays. Some scientists propose that when the solar wind is weak during periods of low sun activity, more of these cosmic rays can penetrate Earth's atmosphere. The hypothesis suggests these rays might seed the formation of low-level clouds by ionizing particles in the air. More clouds could mean more sunlight is reflected back into space, potentially contributing to a cooling effect on the planet. This theory, while compelling, remains an active and debated area of research, illustrating how difficult it can be to untangle the myriad of influences that shape our climate from one another. Then there are the truly catastrophic events, the astronomical wild cards that can rewrite the rules in an instant. The most famous and controversial proposal of this kind is the Younger Dryas impact hypothesis. This theory suggests that around 12,800 years ago, just as the world was emerging from the last ice age, a comet or asteroid exploded in Earth's atmosphere above North America. The proposed result was a continent-wide firestorm, followed by a vast dust cloud that blocked out the sun and plunged the northern hemisphere back into glacial conditions for over 1,000 years. Proponents point to a thin layer of sediment from that time that contains nanodiamonds, shocked quartz, and other materials often associated with extraterrestrial impacts. While this hypothesis is hotly contested and far from universally accepted, it underscores a crucial point. Our planet's history can be shaped by sudden, violent events from beyond our world, interruptions to the more predictable cycles of tilt and orbit. Despite these other fascinating influences, Earth's axial tilt retains its central role because of its predictable, cyclic nature. We can calculate its variations with extraordinary precision backwards and forwards in time for millions of years. This predictability allows scientists to create powerful models that can separate this signal from the noise of other factors. To truly appreciate the stability that this tilt provides, we need only look to our planetary neighbor, Mars. The red planet experiences axial tilt variations that are nothing short of chaotic. Without a large moon like ours to stabilize its orientation, Mars's tilt can swing wildly from as little as 15 degrees to as much as 35 degrees over periods of hundreds of thousands of years. These extreme shifts would create climate chaos on a scale we can scarcely imagine, likely vaporizing its polar ice caps during high tilt periods and refreezing them during low tilt phases. This dramatic comparison highlights a profound truth. Earth's relatively stable tilt, gently moderated by our moon's gravitational pull, is a cornerstone of the long-term climate stability that allowed life to flourish and evolve over billions of years. By widening our view to include these broader cosmic contexts, we gain a deeper appreciation for the intricate dance of forces that govern planetary change. The story of our oceans rewriting their borders is not a simple one-note melody, but a complex symphony conducted by gravity, played by orbital cycles, and occasionally interrupted by stellar variations or cosmic accidents. Yet, amidst this complexity, the rhythmic, predictable wobble of Earth's axis remains the dominant bassline, the steady pulse that sets the tempo for the ice ages and the warm periods for the falling and rising of the seas. It is the central mechanism through which the motions of our solar system are translated into the environmental transformations that have shaped and continue to shape the destiny of our world and every living thing upon it. Faced with the relentless advance of the ocean, our ancestors did not simply surrender their homes to the waves. They responded with a breathtaking display of ingenuity and resilience. Long before the advent of modern engineering, communities living on the front lines of sea level rise developed sophisticated strategies to adapt to their rewriting world. In the swampy deltas of Southeast Asia and the Pacific, the solution was to literally rise above the water. Ancient societies constructed entire villages on towering wooden stilts, building their homes on elevated platforms that kept them safe from tidal surges and seasonal flooding. This wasn't a temporary fix. It was a way of life that allowed them to thrive in dynamic environments where land and water constantly negotiated their borders. Even more remarkably, some cultures didn't just adapt to the existing landscape, they created entirely new ones. Across the Pacific, from the artificial islands of Nan Madol in Micronesia to the centuries-old floating villages of the Uros people on Lake Titicaca, humans demonstrated an incredible ability to build sustainable habitats directly on the water, using local materials like reeds, stone, and coral to forge their own territories in defiance of the rising seas. Perhaps the most profound adaptation was not in building stationary defenses, but in mastering the art of movement. The greatest navigators in human history, the Polynesians, likely honed their incredible open ocean wayfinding skills in response to environmental pressures, including the submergence of coastal homelands across Southeast Asia. Their legendary double-hulled voyaging canoes became vehicles of survival, carrying entire communities, along with their plants and animals, across thousands of miles of open ocean to discover and settle new islands. This was not a haphazard flight, but a deliberate, planned migration fueled by an intimate knowledge of wind, waves, and stars. Similarly, the very foundation of Venice, that iconic city of canals, is a story of adaptation. Its first settlers in the 5th century, fleeing invading armies on the mainland, sought refuge in the marshy, protected islands of the Venetian lagoon. What began as a defensive move became a centuries-long project of engineering, driving millions of wooden pilings into the soft sediment to create a stable foundation for a magnificent city that exists in a delicate balance with the water that surrounds it. These historical examples share a common thread, a flexibility of mind and a willingness to innovate, proving that the most successful survival strategy was often to work with the water rather than against it. Today, we face the same fundamental challenge, but we wield a vastly different toolkit. Modern coastal engineering has created formidable barriers against the ocean's advance. Massive seawalls and storm surge barriers, like the monumental Meeslankering in the Netherlands or the Thames Barrier in London, are feats of engineering designed to protect millions of people and trillions of dollars in infrastructure from the worst of the sea's fury. Land reclamation has reached staggering scales, with projects like the Palm Jumeirah in Dubai or the ongoing expansion of Singapore literally reshaping coastlines to create valuable new real estate from the seafloor. And looking to the future, architects and engineers are pioneering the next frontier of aquatic habitation, floating cities. Concepts like Oceanix Busan in South Korea envision sustainable, resilient communities built on modular platforms that can rise with the sea, a modern echo of those ancient stilt houses and artificial islands, but scaled for the climate crisis. The most powerful lessons, however, come from those who have been engaged in this battle for generations. The Netherlands is a nation that exists largely because of human engineering. Nearly a third of its land lies below sea level, wrested from the North Sea through a complex system of dikes, pumps, and windmills stretching back 1,000 years. Their entire history is a masterclass in adaptation. After a catastrophic flood in 1953 killed nearly 2,000 people, the Dutch launched the Delta Works, one of the most extensive series of FLOOD Chinese letter structures ever built. But in recent decades, they have undergone a profound philosophical shift. They realized that simply building higher and stronger walls was a losing battle against a rising ocean. This led to the revolutionary concept of room for the river. Instead of fighting to constrain every waterway, they are now strategically allowing rivers to flood into designated areas, creating parks and wetlands that safely absorb floodwaters during storms. This approach of living with water, rather than constantly fighting it, is now a guiding principle for climate resilience worldwide, showing that the most sustainable solutions often involve mimicking nature's own processes rather than trying to dominate them. This long view of history provides a crucial insight. The Earth's axial motions are immense, unstoppable forces that operate on a timescale far beyond human control. We cannot stop the planetary wobble that contributes to sea level rise. It is a fundamental part of our world's mechanics. What we can control is our response. The lesson from our ancestors is not that we must abandon our coasts, but that we must design our presence there with humility, flexibility, and a deep respect for the power of the ocean. This means moving beyond rigid, permanent defenses and embracing adaptive, malleable solutions. It means restoring natural buffers like mangrove forests, salt marshes, and coral reefs that protect coastlines while enhancing biodiversity. It means making difficult but necessary decisions about strategic relocation for the most vulnerable communities, a process often called managed retreat. By studying how past civilizations coped with the reality of rewritten borders, we learn that survival is not about winning a war against the sea, but about learning to dance with it, designing a future where human ingenuity and natural forces can find a new, sustainable equilibrium. This profound connection to place is a fundamental part of the human experience, a deep-seated bond that forms the very bedrock of our identity and cultural memory. When that place is physically erased, consumed by a rising ocean that no wall or plea can hold back, the resulting trauma reverberates through generations, leaving a psychological wound that is as real as any physical displacement. This isn't merely about losing property or relocating to higher ground. It is the catastrophic unraveling of a world, a severing of the sacred ties that bind a people to their ancestors, their history, and their understanding of their own place in the universe. The myths of sunken paradises like Atlantis or Kandam are far more than fantastical stories. They are the enduring echoes of this profound grief, a collective cultural mechanism for processing a loss so immense it can scarcely be comprehended. These narratives transform a geological event into a moral or spiritual lesson, a tale of divine punishment or a forgotten golden age, allowing a community to encapsulate its trauma in a story that can be passed down, preserving the memory of what was lost even as the physical evidence vanishes beneath the waves. We can see this ancient grief mirrored with heartbreaking clarity in the modern world, where the slow-motion catastrophe of human-caused climate change is forcing nations to confront their own disappearance. For the people of low-lying island nations like Tuvalu, Kiribati, and the Marshall Islands, the rising sea is not an abstract future threat. It is a present-day reality that infiltrates every aspect of life. They are experiencing a specific and deeply distressing form of psychological pain known as solastalgia, a term coined to describe the emotional anguish caused by environmental change happening to one's home environment while they are still directly connected to it. It is a feeling of homesickness while you are still at home, because the home you know is being systematically dismantled around you. The saltwater poisoning the gardens their families have tended for centuries, the king tides that regularly flood homes and schools, the very graves of their ancestors being washed away. Each event is a fresh cut, a reminder that their entire world, their culture, and their nationhood are living on borrowed time. This relentless environmental erosion creates a pervasive sense of powerlessness and existential dread, a mourning for a future that is being stolen before it can even happen. Historically, this deep-seated connection to lost lands became woven into the very fabric of cultural expression, manifesting in rituals, art, and oral traditions that served as both a memorial and a tool for resilience. The Aboriginal peoples of Australia, whose connection to country is a central tenet of existence, have dreamtime stories that meticulously describe coastlines and landscapes that were drowned by rising seas thousands of years ago. These aren't vague legends, they are precise, place-based maps of a world that no longer exists, a testament to the power of oral history to preserve geographical truth across millions of generations. Similarly, the ritual ceremonies and intricate art of many coastal cultures often feature symbols of the sea as both a life-giver and a destroyer, a dualistic representation of a force that provides sustenance but also holds the terrifying power to reclaim everything. This cultural embedding of loss and adaptation is a form of psychological armor. By ritualizing the trauma, a community can achieve a measure of control over the narrative, transforming a story of victimhood into one of survival and enduring spirit. It is a way of asserting that while the land may be gone, the people and their memory are not. This emotional dimension is the crucial, often overlooked, human heart of the story of axial tilts and rising seas. Geology gives us the mechanism, the wobble, the melt, the inexorable rise of the water, but it is the human response that gives the event its deepest meaning. The physical rewriting of a coastline is simultaneously a rewriting of human identity, forcing a painful recalibration of who a people are when the land that defined them is taken away. It underscores a vital truth, that preparing for a future of rising oceans is not just an engineering challenge of building seawalls and moving infrastructure. It is equally, and perhaps more importantly, a psychological and cultural project. It requires creating spaces for collective grief, for the preservation of stories and memories, and for the mental and spiritual adaptation to a new reality. The resilience of a community is not measured solely by the height of its defenses, but by its ability to carry its identity forward, to find ways to sing the old songs and tell the old stories even on new ground, ensuring that when borders rewrite themselves, the soul of a people is not lost to the depths alongside their land. This constant redrawing of the world's map by rising and falling seas didn't just change where humans could live, it fundamentally reshaped the very tapestry of life on Earth, creating and destroying the planet's most vibrant biological treasure troves in a relentless cycle. As ocean levels fluctuated with the rhythmic pulse of Earth's axial tilt, the geographical distribution of species was thrown into a state of continuous flux. Lush, low-lying coastal plains that served as vast, interconnected habitats were suddenly severed by invading saltwater, isolating populations on newly formed islands. Conversely, when seas retreated during glacial periods, land bridges emerged, allowing previously separated species to meet, mingle, and compete in entirely new ways. This dynamic process of fragmentation and connection acted as a powerful engine of evolution, but it was also a ruthless arbiter of extinction, with the fate of entire species hanging in the balance of their ability to follow the shifting borders. A stunning example of this evolutionary engine at work is likely the Amazon basin, home to the greatest concentration of biodiversity on the planet. The mind-boggling variety of life found there may be a direct legacy of these ancient sea changes. During periods of high sea level, much of what is now the Amazon rainforest was actually a vast inland sea or a massive flooded basin, often called the Amazonian Sea. This immense body of water would have fragmented the once continuous forest into a scattered archipelago of isolated islands. On these isolated landmasses, animal and plant populations were cut off from one another. Over thousands of generations, each isolated group evolved independently, adapting to the specific conditions of their island and giving rise to new species. Then, when sea levels fell again, the islands reconnected, allowing this incredible new diversity to mix and spread across the reformed continent. This cycle of isolation and reconnection, repeated over multiple glacial-interglacial cycles, essentially acted as a species pump, dramatically accelerating the rate of evolution and creating the breathtaking biological richness we see today. It's a powerful demonstration of how the planet's physical transformations, driven by its wobble, directly write the genetic code of its inhabitants. However, for every story of evolutionary innovation, there is a counter-narrative of tragic loss. While some species flourished in this changing world, others faced insurmountable obstacles. The most vulnerable were those with specialized habitats and limited mobility. Giant, slow-breeding animals like the mammoths and giant ground sloths we discussed earlier were often trapped on shrinking landmasses. But countless smaller, less charismatic species also vanished without a trace. Think of a small mammal adapted to the specific soil and plants of a particular coastal valley, or a flightless insect that thrived in the unique microclimate of a now drowned forest. When the waters rose too quickly, these creatures had nowhere to go. Their entire world simply disappeared beneath the waves, leaving no refuge and no time to adapt. The fossil record is littered with these silent tragedies, entire unique ecosystems erased by the ocean's advance, their stories forever lost. This starkly illustrates that the same process that creates new life can also be an agent of utter destruction, with the speed of change being the critical factor that determines survival or oblivion. Tragically, this ancient drama is playing out once again on a global scale, but this time the primary driver is human activity, not planetary tilt. Modern climate change, fueled by greenhouse gas emissions, is causing sea levels to rise at an alarming rate, threatening the world's remaining biodiversity hotspots. Coastal ecosystems like mangrove forests, salt marshes, and seagrass beds are on the front lines, being squeezed between the advancing ocean and human development on shore. These areas are not just scenic, they are vital nurseries for countless fish species and crucial buffers against storm surges. Even more acutely threatened are coral reefs, the rainforests of the sea. Corals are highly sensitive to both water temperature and depth. As sea levels rise, deeper water can block the sunlight they need to survive, while the same warming that melts the ice also causes catastrophic bleaching events, where the corals expel their symbiotic algae and turn white, often leading to death. The parallel to past extinction events is chillingly clear, only now the changes are occurring orders of magnitude faster. The crucial lesson we must take from Earth's deep history is that the key to survival is connection. In the past, species that could migrate across connected landscapes had a fighting chance. Today, our modern world is a patchwork of isolated habitats fragmented by cities, farms, and highways. Conservation efforts must therefore prioritize creating and protecting wildlife corridors, continuous stretches of natural landscape that allow animals and plants to move freely in response to changing conditions. This isn't just about saving individual species, it's about maintaining the genetic diversity that allows populations to adapt. A population of trees that can slowly spread northward as temperatures warm carries within its genes the variations that might allow it to survive in its new home. By studying how life navigated the planetary changes of the past, we are given a blueprint for the future. We must become active stewards in facilitating this great migration, consciously designing a planet where life has the room and the pathways to adapt, ensuring that the incredible biological heritage shaped by millions of years of planetary wobbles is not lost in a mere century of human influence. Imagine a world where the most valuable piece of real estate wasn't a city or a mine, but a simple path. For thousands of years, the vast plain known as Doggerland provided exactly that, a flat, easily traversable highway connecting the European continent to the island of Britain. This was no minor footpath, it was a superhighway for the movement of people, animals, and most importantly, goods and ideas. Communities could trade flint from England for amber from the Baltic without ever setting foot in a boat, their economies intertwined across a continuous landscape. Then the waters came. As the seas rose, this critical land bridge didn't just get wet, it was systematically erased mile by mile until the North Sea swallowed it whole. In a geological blink of an eye, a direct overland trade route of immense economic value vanished beneath the waves. The cost of doing business was suddenly transformed. Where once a merchant could walk their goods across solid ground, they now faced the treacherous and expensive challenge of building a vessel, hiring a crew, and braving the open ocean. This single environmental catastrophe didn't just change the map, it fundamentally rewired the economic circuitry of an entire region, forcing a dramatic and permanent pivot from land-based to maritime commerce. This pattern of economic reinvention, forced by the ocean's hand, repeated itself across the globe. On the southeastern coast of India, the ancient port city of Mahabalipuram thrived as a bustling hub of the Pallava kingdom, its ornate temples and busy docks a testament to its wealth and connectivity. Legend speaks of 7 such pagodas, but today, only one stands prominently on the shore. For centuries, the others were thought to be mere myth, until a tsunami in 2004 pulled back the curtain of water to reveal the truth. Submerged structures and scattered ruins lying offshore provided stunning evidence that a significant portion of this ancient trading center now lies on the seafloor. The rising seas that consumed these districts didn't just erase buildings, they eroded the city's economic foundation. As the waterfront advanced, the vital dockyards and warehouses were drowned, forcing the city's commercial heart to retreat inland or shift to more viable ports along the coast. This relocation wasn't merely a logistical headache. It represented a massive, unplanned transfer of economic capital and infrastructure, disrupting established trade networks and redistributing wealth and influence to new population centers that were suddenly better positioned on the new coastline. Out of this chaos of rewritten shores, new naval superpowers were born. The Phoenicians, who established a trading empire that stretched across the entire Mediterranean, are a prime example. While their rise was influenced by many factors, their success was built upon a masterful understanding of the sea as the ultimate highway. In a world where land routes could be long, dangerous, and controlled by rivals, the open water offered a direct path to resources and markets. They didn't just use the sea, they mastered it, developing advanced shipbuilding techniques and navigational skills that allowed them to transport valuable goods like Tyrian purple dye, cedar wood, and glassware from city to city. Their economic model was one of pure adaptation, turning the environmental challenge of a water-dominated world into their greatest strategic advantage. Similarly, the incredible expansion of the Polynesian people across the vast Pacific Ocean can be seen as the ultimate story of economic adaptation to rising seas. As coastlines changed in Southeast Asia, these unparalleled navigators took to the waves not just for trade, but for colonization, carrying their entire economic system, based on transplanted crops and livestock, with them in their double-hulled voyaging canoes. They created a sustainable, maritime-based economy that spanned thousands of islands, a testament to how economic resilience can be forged through innovation in the face of environmental change. The enduring lesson from these historical transformations is that economic survival has always depended on a society's agility, its ability to abandon outdated models and embrace new ones dictated by the physical world. A civilization wedded to its drowning ports would fail, while one that invested in a navy and new trade routes would flourish. This historical insight carries a profound warning for our modern global economy, which is overwhelmingly concentrated along today's coastlines. Major financial hubs, critical shipping ports, and dense population centers are all positioned based on a sea level that has been stable for millennia. As modern climate change triggers a new era of rising oceans and intensified storms, we are facing a similar, though vastly accelerated, period of economic rewriting. The challenge is no longer just about building higher seawalls. It's about fundamentally rethinking the geographic distribution of our economic assets. This means investing in sustainable infrastructure further inland, developing new supply chains that are less vulnerable to coastal disruption, and fostering economic diversity so that a hurricane or flood in one region doesn't cripple global trade. The past shows us that environmental shifts are not just ecological events. They are powerful economic revolutions that demand innovation, flexibility, and a willingness to chart a completely new course. But as we reach out to touch these sunken worlds, our hands are met with a complex web of ethical questions that have no easy answers. The thrill of discovery is immediately tempered by a profound responsibility. Who truly holds the rights to a city that vanished beneath the waves thousands of years ago? Is it the nation whose territorial waters now cover it? The academic institution that funds its excavation? or the descendants of the very people who built it, whose cultural and spiritual connection to that place may have endured long after the last stone was submerged. This isn't merely an academic debate, it's a deeply human one, pitting the pursuit of knowledge against the respect for ancestral memory and the sovereignty of living cultures. International frameworks like the 2001 UNESCO Convention on the Protection of the Underwater Cultural Heritage provide a crucial starting point, establishing principles like preservation in situ as a first option and the prioritization of knowledge over commercial gain. Yet these well-intentioned guidelines often collide with the messy realities on, or rather under the water. An ancient trading vessel laden with artifacts might lie in international waters, its legal status ambiguous. A Neolithic settlement off the coast might be claimed by a modern indigenous group whose oral histories have spoken of its existence for millennia, even as a national government claims jurisdiction. These disputes reveal a fundamental tension. The ocean's past is a global scientific treasure, but it is also composed of countless local human stories, each demanding recognition and respect. This ethical landscape becomes even more fraught when we consider the accelerating threat posed by our own era. Climate change and its attendant forces, stronger storms, acidifying waters, and rising sea levels are not just future threats, they are actively eroding these underwater archives right now. Sediments that have protected wooden structures for millennia are being swept away by intensified currents, exposing them to rapid decay and destruction. The very process of oceanic rewriting that buried these sites is now being reversed, not by natural cycles, but by human influence, threatening to erase them forever before we even have a chance to study them. This crisis has created a perverse race against time, but it has also emboldened those who see not knowledge to be gained, but profit to be made. Looters armed with advanced sonar and dredging equipment often descend on newly exposed sites, tearing through layers of history to grab sellable artifacts, destroying the precise context that gives those objects their true meaning and value. A beautifully crafted vase pulled from the mud and sold on the black market is a tragedy. It becomes a beautiful but silent object. Its story, who made it, who used it, what it can tell us about trade, belief, and daily life, is lost forever in the scramble for profit. This places archaeologists in a heartbreaking dilemma: to excavate quickly to save what they can from both natural and human predators, potentially cutting ethical corners in the process, or to adhere to slower, more methodical and inclusive processes, risking the total loss of the site. Navigating this ethical minefield requires a fundamental shift in how we approach exploration itself. The old model of the solitary treasure hunter or the distant academic institution swooping in to extract finds is not just ethically bankrupt, it is scientifically short-sighted. The most progressive projects today are built on a foundation of community collaboration from the very beginning. This means involving local and indigenous communities not as an afterthought, but as essential partners in every stage of the process, from planning and discovery to excavation, interpretation, and curation. Their traditional knowledge can be invaluable. An oral history about a legendary drowned village can literally guide researchers to a specific location, saving years of fruitless searching. More importantly, this collaborative approach ensures that the human stories behind the geology are honored. A discovered artifact isn't just a data point. It might be a sacred object, a direct link to an ancestor, a piece of a living cultural identity that was interrupted, not ended, by the rising seas. By sharing authority over these discoveries, we move from a paradigm of extraction to one of stewardship. The goal is no longer to simply fill a museum case, but to weave these reclaimed threads back into the cultural fabric of the communities they were torn from. enabling a healing of historical trauma and a reconnection with a past that was thought to be lost. Ultimately, the ethical excavation of these drowned worlds is about more than preserving pottery and bones. It's about honoring a covenant between the past and the future. Every time we carefully raise an object from the seabed, document its position, conserve it, and study it with the consent of its cultural heirs, we are making a statement. We are saying that the story of humanity is not a commodity to be bought and sold, but a sacred narrative to be understood and shared. It is a recognition that the forces that rewrote the planets, coasts, the axial tilts, and the rising seas did not erase the people who lived there. Their experiences, their adaptations, and their losses are an indelible part of our shared history. By choosing an ethical path of discovery, we ensure that in our quest to understand how the Earth changed, we do not forget the people who endured that change, and we guarantee that the secrets we uncover from the deep serve to enlighten all of humanity, not just to enrich a few. Unlocking the full story of Earth's dramatic transformations demands we break down the walls between academic disciplines. No single field holds the master key to these planetary mysteries. Instead, it is the powerful synergy between them, the unexpected conversations between geologists and anthropologists, the shared data between climatologists and archaeologists, that finally allows us to see the complete picture. Think of it like a grand intellectual orchestra. Each instrument has its own beautiful part to play, but the true magic, the profound revelation, only emerges when they all play in harmony. A sediment core pulled from the ocean floor might tell us when sea levels rose, but it takes the discovery of a submerged village within that same sediment layer to show us who was affected. An ice core from Greenland can reveal a precise timeline of ancient atmospheric changes, but it is the Aboriginal Dreamtime story describing a coastline that vanished thousands of years ago that gives that data a human heartbeat, transforming cold numbers into a shared cultural memory. This is where science and storytelling cease to be rivals and become the most powerful of allies, each validating and giving depth to the other. This collaborative spirit is supercharged by modern technology, which acts as a universal translator between these different fields of study. Satellite altimetry and LiDAR, tools born from aerospace engineering, are now indispensable to archaeologists. They allow us to digitally strip away millions of gallons of seawater to map the ghostly river valleys and sunken coastlines of lost continents like Doggerland or Sunderland with breathtaking precision. Meanwhile, powerful climate models running on some of the world's most advanced supercomputers can ingest geological data, astronomical calculations, and archaeological evidence to simulate ancient environments. Scientists can essentially run experiments on the past, inputting different variables for axial tilt or ice sheet volume to see which scenario best matches the evidence we've dug up from the ground and pulled from the sea. This isn't just guesswork, it's a rigorous, data-driven form of time travel. Incredible partnerships like those between historians and NASA scientists demonstrate this perfectly. By applying satellite-based remote sensing technologies developed for observing other planets, researchers can now identify subtle chemical changes in soil or vegetation that mark the location of long-buried human settlements on Earth, guiding archaeologists directly to a new dig site from hundreds of miles in space. The ultimate reward for embracing this interdisciplinary approach is a holistic, deeply nuanced understanding of our planet's history. We move beyond simple cause and effect and start to appreciate the complex, interconnected web of relationships that shape our world. A climatologist can explain the mechanism of an axial tilt shift. An archaeologist can show you the tools left behind by refugees fleeing the resulting floods, and a folklorist can share the myth that grew from that traumatic event. Individually, these are fascinating facts, but woven together, they form a rich human tapestry that tells us not just what happened, but what it felt like and how it forever altered the course of human civilization. This unified perspective is our most valuable tool for facing the future. The challenges of modern climate change and sea level rise are not purely engineering problems or political issues. They are complex, multifaceted crises that demand a similarly integrated response. By learning how to think across boundaries, by valuing both hard data and human experience, we cultivate the innovative, flexible mindset needed to develop comprehensive solutions. The greatest mysteries of our planet refuse to be confined to a single textbook. They yield their secrets only to those willing to collaborate, to listen, and to learn from every source of knowledge available. From the tiny bubbles of ancient air trapped in polar ice to the epic tales of global floods passed down through generations, the story is undeniable. Our planet is not a static stage upon which history unfolds, but a dynamic, living participant. Its gentle, rhythmic wobble on its axis has been a silent conductor, orchestrating vast climatic symphonies that have, time and again, commanded the oceans to rewrite their very borders. We have walked across lands now buried beneath hundreds of feet of water, and built our homes on shores that would one day vanish into the abyss. This relentless transformation has sculpted the course of evolution, determined the fate of empires, and forged the resilient spirit of humanity itself, forcing innovation and adaptation in the face of unimaginable change. These profound events from our deep past are not merely fascinating history, they are an urgent playbook for our present. They demonstrate with terrifying clarity that Earth's climate system is built upon tipping points and feedback loops, where a small nudge can unleash an unstoppable cascade of consequences. The same forces that drowned Doggerland and inspired the legend of Atlantis are not dormant relics. They are active processes, and we have now become the primary agents accelerating them. Our actions are replicating the effects of a drastic axial shift at a pace the planet has not witnessed in millions of years, challenging the very stability that allowed our civilization to flourish. The ancient evidence screams a warning we can no longer ignore: to respect the delicate balance of the systems that govern our world. This knowledge, however, is not a counsel of despair, but a powerful catalyst for hope and action. We are the first generation to see this intricate planetary machinery with such clarity, to understand both its immense power and its profound fragility. Unlike our ancestors who could only interpret the rising tides as the wrath of gods, we possess the science, the technology, and the global connectivity to choose a different path. The lesson from the past is not that we are doomed, but that we must become as adaptable and resilient as those who came before us. It is a call to innovate with sustainable energy, to design smarter, more flexible cities, and to protect and restore the natural barriers, the mangroves, wetlands, and reefs, that have always been our first line of defense against the sea. Our journey through deep time reveals a final, beautiful truth: that exploration is never just about the past. It is about understanding our place in a grand, ongoing story. Every submerged village rediscovered, every ancient climate datum decoded, adds another piece to the puzzle of who we are and the world we inhabit. It connects us across millennia to the hopes and fears of people who faced challenges as great as our own. So we turn the question over to you: which lost civilization or ancient mystery captures your imagination? Is it the sunken ruins of Dwarka, the enigmatic builders of Göbekli Tepe, or the vast, unexplored landscapes that once connected continents? Share your thoughts in the comments below. Let's keep this conversation going. If you've enjoyed this journey to the edges of history and science, be sure to like this video and subscribe to our channel. Together, let's keep exploring the deep histories that bind us all to this amazing, ever-changing